Hi everyone. In this lecture, we will start with our discussion of the wireless channel models. Now, why do we need to understand wireless channel models? Is that eventually, as we discussed, the bit error rate in a cellular communication system depends upon what is the total power that you receive at your handset or your mobile station from the base station. So, therefore, understanding the wireless channel models will help you predict what is the power level that you will receive at your handset. Now, you should understand that the moment we have a problem like this, every user is going to experience a different channel. And we need to exactly know everything in between the base station and the mobile station to exactly predict what will be the loss. So, since we will not know that, we will adopt the statistical models. So, obviously, this is something you're already aware of. So, if you're going to roll a dice, if you know the phase on which you are applying the force, and what is the force you are applying, and if you know the elasticity of the material of the dice and the air friction and everything, and also the coefficient of restitution as the dice lands on the earth and on the surface, and how many times it will undergo, how many times it's again going to rise and come back, rise and fall back, and eventually all that. If you know everything, you can exactly predict what's going to be the outcome of the dice. But then we say, okay, we don't want to do all that. Instead, we resort to probabilities. Okay, so we resort to probabilities. We conduct experiments and then come up with we know that outcomes are only finite. You know that there are only finite number of outcomes. There are only 6 possible outcomes in a dice. So we'll come up with a probability distribution of what is the probability that the dice is going to give a certain output. Based on that, then we'll predict, if let's say the dice is used in a game, we'll predict the outcomes of the game using this probability and statistics. So in a similar way, we'll adopt statistical models for the wireless channels, as we will see. To begin with this, there are 3 main fundamental mechanisms of wireless transmission. I mean, what happens when an electromagnetic wave reaches your cellular phone? There are 3 mechanisms. I'll start talking about the mechanisms as we go into the lecture. But I'll just very briefly start that the fundamental mechanisms are simply electromagnetic waves are like light waves, so they'll undergo the same phenomenon that light waves will undergo. So you'll have reflection, you will have diffraction, okay, and you're also going to have scattering. So these are the 3 phenomenon that's going to happen. We'll see a little bit what does each one of these phenomenon mean, and what effect does it have on the channel models. Okay, so now the main thing why I discussed about these 3 mechanisms of signal traveling, the signal propagation, is that at a cellular phone, for example, let's say you are talking inside a house. So you have a base station which is transmitting the signal, which might reach to the house directly from the antenna, or since an electromagnetic wave, let's assume it's an isotropic radiator, it is radiating in all directions. So it can have a path which is reflecting and entering the house, okay, or it can have some other paths as well. It can have many paths which is reflecting and entering the house. Now the thing is, if you are going to move by small dimensions, when I say small dimensions, the dimension should be compared with the wavelength of the transmitted signal. Lambda is the wavelength of the transmitted signal. That we know. Once you know the carrier the velocity of the light is c divided by the carrier frequency will give you lambda. Okay, so once you know this lambda, the wavelength of the carrier frequency, we measure the distances in terms of the wavelength. If let's say you are moving few wavelengths, less than 5 lambda or 10 lambda, few wavelengths, 10 lambda, 12 lambda, less than that, then these 2 paths are not going to change much. Okay, these 2 paths are more or less going to remain the same. Okay, but what will change internally is that once the signal enters the house, it can reflect off the walls, it can scatter on some uneven objects, and then multiple rays can be generated, and you will actually receive a huge number of components, and as you are walking inside the house, those components also will change. So now you have to classify the components which are going to reach the mobile phone. That's why this modeling is something that we are going to discuss. So one is called the large scale effects, where these things, the reflection paths and all that, they don't change at all if the phone is moving few wavelengths. Say for example, if the phone is fully moving from here to a different location altogether, then yes, the path, reflected path itself, the large scale path itself changes. And that distance is several wavelengths, 40 or tens of wavelengths, 50 wavelengths or so. When you're moving very large distances away from the base station, then you can use, then the large signal path itself will change. Otherwise, for small distances, that path is not going to change. Now, what is the problem? Why are we caring about multiple paths adding up? So, in wireless communication, in a line of sight communication, there is one transmitter and one receiver, and there is only one path for communication. But in a wireless communication, for example, if you assume an isotropic radiator, power can radiate in all directions. So, it will, for example, if there is a smooth ground surface, it can reflect and reach this. Okay, or let's say there is a surface on top of you, it can actually go through this and then reach you. Now the problem is this is called multipath propagation. The receiver is going to receive multiple paths, signal from multiple paths of the same source. Now these multiple paths can add constructively or destructively. Okay, so when it adds destructively, you are going to lose signal. So that's what we call fading. Your signal power will start reducing. Okay, so now these effects of fading or the loss of signal power because of these multiple paths, we have to classify them into two different types. One is the large signal propagation or large scale effects. Okay, not large signal but large scale effects. And this happens, this is about if the receiver is moving by several wavelengths, 40 wavelengths ahead or more than that, several tens of wavelengths when he is moving, then the paths that the path that the signal takes to reach the receiver from the base station itself will change. That path itself will change. I mean, signal directly coming from the base station, that path itself will change. So those changes will cause a different effect on the signal received by the receiver. So to characterize that, we use what we call large scale effect. I mean, we call that as the large scale effect. Now, a small scale effect is nothing but if you are moving for very short distances, as I gave an example, let's say you are moving inside a small room. You are just moving inside a small room, few wavelengths away, not even tens of wavelengths, but less than 10 wavelengths. In that case, the reflected paths again will change. I mean, because the entire signal you will be receiving, there is no line of sight path in the system at all if you are inside a room. Everything is purely based on reflections and scattering and so on, or even diffraction. So we will see what it is. Okay, scattering, diffraction and reflection, these are the three mechanisms by which the signal will reach, and that will change depending on where you are moving in your house itself. So those again, you will have some kind of signal power variations, because the signal can suddenly act destructively and you will get very low power. Suddenly when you move one more wavelength away, you might get a high power. So those are called small scale effects. So there are two kinds of effects which you have to model into a wireless channel. So first thing is what we call the large scale effects, which is what we will be discussing right now. This tells you the average power that you will be receiving at the receiver, okay, at a certain distance r from the base station. So if you are away at a distance r from the base station, that's the average power will come from the large scale effect analysis. We will do an analysis that is also statistical analysis, and that will give you the large scale power that your mobile station receives. In addition to that, we will model the losses because the base station, the mobile station moving inside the house for very small wavelengths. That we will model it in small scale effects. Okay, so then if both of the effects has to be taken into account when you are trying to compute the total received power at the mobile station. So here I have taken a picture from your textbook. It shows this graph here, the one in the curve, the slowly varying curve actually shows the large scale fading or the large scale power. This is actually TR separation, that is transmitter and receiver separation. In here he has given it in meters. Okay, so you can see the large scale power remains more or less constant. See, like for example, if you are moving for very small distances here, the large scale power which is shown by this curve, okay, which is this curve here, which is varying very, very slowly. It doesn't have much variations there. Okay, because the large scale path is not going to change much, as we discussed, when you are going to move by small distances. But if you see the small scale power here can have a sudden dip here. It's suddenly becoming very low here, and then immediately after some time it's going to become high. Okay, so this is what we call small scale variation. So now we will actually try to come up with mathematical models to capture the effect of both these. Eventually what we are interested is a combination of both. We have to understand both large scale effects and small scale effects. So keeping this in mind, I'll start with a lecture of the wireless channel models. So I'll start with the basic point where we have already discussed this, which is the line of sight communication. So we know that in a line of sight communication, the power that is radiated at a distance r, the power received at a distance r, if you assume the transmitter antenna, this is for an isotropic antenna, okay, this result is true for an isotropic antenna, transmit antenna, okay, and an isotropic receive antenna, it's able to fully receive the entire power. So that's an isotropic receive antenna. In that case, with antenna gains equal to 1, GT and GR are equal to 1. So we will discuss how to characterize them now in this lecture. Okay, so in the previous lectures I have just very briefly introduced them. We will now probably go a little bit deeper in these lectures. So we know this is the expression for the power that is received at a distance r away from the transmitter. So r is the distance from the base station to the mobile station, or it's often called TR separation, transmit receive separation. Now to understand this result more intuitively, often in some engineering textbooks they would use the standard procedure. So what they'll do is let PT be the total power transmitted by an isotropic source. So this is going to be transmitting equal power in all directions on a sphere. So PT by 4 pi r square is going to be the power density on the surface of this sphere at a distance r away from the transmitter. That if I multiply by AE, that's the receive antenna's area, AE is the aperture area or the receive antenna's area, I can get the value of the receive power. Okay, now that's what it's often derived that way. I mean, now if you see, there is a very interesting result for the aperture area and receive antenna gain are related by this result. The gain of the receive antenna is given by 4 pi AE times lambda square. So I'm just going to use the previous result, which is nothing but PT by 4 pi r square into AE. Now AE is nothing but GR into lambda square by 4 pi. Okay, so in the transmit antenna, I have assumed the gain, transmit antenna gain to be 1, which is GT equals 1 in my analysis. But generally you will have to multiply this power by GT. We will talk about why should we multiply by GT in a few moments. But right now we can assume that the transmit antenna power just gets a boost by the gain factor GT. For an isotropic antenna, GT is 1. So GT PT by 4 pi r square is the power density. That multiplied by area here, so this is nothing but area here, so lambda square GR by 4 pi is nothing but the aperture area. So if I combine these two results, I am going to get this expression. This is the well-known expression that we are aware of for the path loss models. Okay, the 4 pi and 4 pi multiplies and you have 4 pi r square. Here the assumption is this result is valid if gain GT and GR are constants. They don't change with frequency. Okay, in that case we can say the received power is actually proportional to lambda square as well. Okay, lambda is the wavelength of the transmitted wave and inversely proportional to the distance. So in this equation there is an additional factor called loss factor L. Okay, this number is greater than 1, greater than or equal to 1. So this is to account for additional losses. Okay, this is the, I have just accounted for transmit and receive gains, but you can also account for additional losses. I mean, it can be the coupling losses from the transmit antenna and the receive antenna. Okay, or it can be even the directional pointing losses, which I'll talk about a little later. So this is the well-known expression which we had used for line of sight communication, how to compute the path loss or how to compute the receive power if you know the distance between the transmitter and receiver. Now this is again an interesting result. I had to discuss this equation in little bit more detail because you have to understand this result. So in the previous lectures I actually started with this expression directly. Okay, so the receive power at a distance, I said this result can be proven. Actually this result comes from basic electromagnetic theory. If let's say we have a wire carrying an alternating current through it, then it can be shown from a distance r far away, that's the far field region distance, the electric field is inversely proportional to the distance r. And the magnetic field is also inversely proportional to distance r. In fact, these contain some additional terms, higher order terms. All those terms can be ignored compared to 1 by r. Okay, you have some 1 by r square and r cube terms which can be ignored in the electric field, and magnetic field has a 1 by r square term which can also be ignored. So the power radiated is simply proportional to E cross H, so which is the product of these two, is proportional to 1 by r square. So that's how you get this expression. Okay. And we also know the expression for gain, the receive antenna gain in this expression is given by 4 pi into aperture area by lambda square. So now let's say I keep the aperture area constant. If I keep aperture area constant, then the received power is going to be Pt Gt by 4 pi r square times the aperture area. That's going to be your received power at a distance r. Now if you look at this expression, if you fix your aperture area, okay, and again Gt, the transmit antenna gain, is also fixed, transmit power is anyways fixed. In that case, if you see, there is no dependence on lambda. Okay, so this is an interesting result, but generally what happens is that your if you look at this expression here, the gain antenna gain for a receive antenna gain, the aperture area is also normally scaled down when your lambda reduces. So here it shows that the gain of an antenna, receiving antenna, increases with wavelength. Okay, increases with reducing wavelength. As lambda reduces, the gain of the receive antenna increases if you have the same aperture area. Okay, but generally what happens is that your antenna's aperture area normally reduces with wavelength. So if you reduce the signal wavelength, we normally reduce the antenna area as well. So that's the whole idea behind going for wireless communications. If you recall, I said the antenna size becomes unreasonably large if you want to transmit low frequency signals, which is why we did modulation to reduce the antenna size. So generally we don't do this, so which is why we normally reduce the area of the antenna. Okay, which is why this result is valid, wherein it shows that for a line of sight free space communication, the received power is proportional to lambda. So lower lambda or higher carrier frequency means you will receive lower power, and it's also inversely related to 1 by r square. So which is again a standard result that we have discussed so far. Okay. So generally we assume the antenna gain to be constant. So that's what I'm trying to say here. Now, what is the region of validity of these models? The region of validity for this model is what we call this equation, the received power or the free space path loss model equation for a line of sight communication is valid in the Rayleigh distance region or in the far field region. Okay, and what is the distance after which this model is valid? So we define what we call as Fraunhofer distance or Rayleigh distance, and we say the distance has to be greater than this number, and that's given by 2d square by lambda. D here is the largest linear dimension of the antenna. Okay, so if you know for example, if it's a rectangular patch antenna, then the largest side is going to be the largest linear dimension. If it's a square, then any one of the sides will be the largest linear dimension of the antenna. Okay, of course, if let's say this number somehow turns out to be less than d or lambda, again that should not be taken into account. You should pick the value which is, you should ensure the distance where you are measuring this radiated power should be greater than 2d square by lambda. In addition to that, it goes without saying that it should be obviously greater than the wavelength of the signal, much greater than the signal's wavelength, and the largest dimension of the antenna again. Okay, if this number, say for example d, turns out to be either less than lambda or d, we should not take that, then we should pick one of these two conditions. Okay, so you should take an intersection of all the three conditions. So when all the three conditions are satisfied, then you will say, okay, this equation is valid and it's in the far field region. Okay, now we will start characterizing antennas. Okay, so that we have to understand a little bit basics about antennas, because we have been writing GT as the transmit antenna gain. So I'll try to explain what that is now. Now let's say we had a radio, an isotropic source. So let me use a different. Let's say we had an isotropic source which radiates power equally in all directions. Then we said that let's say there was a mobile phone located in this region, it's going to receive only a very small fraction of the total radiated power. So I can say it is Pt by 4 pi r square times the aperture area, right? If you see, if your aperture area is anyways very, very small to begin with, so the radius of where the cell phone is, it's going to be really, really large. The radius is much larger compared to the aperture area. So you're going to receive really, really low powers. Now instead of that, let's say what I do is, the radiating source, I somehow introduce some kind of an obstacle so that whatever power is radiated in this side, I can somehow re-radiate it in this direction itself, so that the power adds in phase. Okay, so now the intensity or the power levels here, it's going to become 2x than what it was previously. The total PT is same. PT is same, but whatever was transmitting in this direction, now I could somehow reflect it and then transmit it in this direction itself, in the same direction. So the power level now becomes twice. Now this antenna, I'm going to say, is better than this antenna. So this is an isotropic radiating antenna or isotropic radiator. So this is an isotropic source which radiates equally in all directions. This antenna, however, is a directional antenna because it's not going to radiate in, it's going to radiate from, so let's assume this is 0 degree. So this is minus pi by 2 to plus pi by 2. It's going to radiate in an angle of minus pi by 2 to plus pi by 2. The total angle of the radiation is 180 degrees. Okay, so I'd say the beam width for this is 180 degrees. Now the gain here, if you see, the transmit power PT is same. Both the powers, both the antennas are receiving the same power to transmit. But since this guy is transmitting with twice the intensity, power is getting added constructively, the mobile phone here will receive twice the power than what it receives here for the same aperture area. So that's what we call GT is the gain. So we define a new term called effective. So let me just finish this. So that term is what we define as GT. So GT is the gain compared to an isotropic radiator. So in an isotropic radiator, you will be receiving a power of PT by 4 pi r square times aperture area. In a directional antenna, you will be receiving PT by 4 pi r square and you will get a gain of GT because that you are directing all the power in the one direction times AE. Okay. So this, if you take the ratio of this power to this power, that term is what we call the gain. And this power here, PT into GT, is what we call effective isotropic radiated power, EIRP. So that's what I've mentioned here. So this term here, EIRP, is nothing but effective isotropic radiated power. Okay, compared to an isotropic radiator, if let's say if PT was the power transmitted by an isotropic radiator, at a distance r, you are going to receive a power 4 pi r square times AE. That's the power you are going to receive. Here I've assumed, I haven't included receive and transmit power. It's an isotropic source, so GT is 1. But in a directional antenna, the power received will be PT GT times by 4 pi r square times AE. So it's more by this factor. So this term, PT into GT, is what I'm going to call as the new power as EIRP, effective isotropic radiated power. Okay, so it's called EIRP. Now, it's often expressed, the effective radiated power, the total effective power, you can either refer it to an isotropic antenna, or because you just need a reference antenna. So whenever you're defining gain, you're defining gain with respect to something. So here you can define GTI as the gain with respect to an isotropic radiator. Similarly, you can define gain with respect to a half-wave dipole antenna. So a dipole antenna will be like this, and it will radiate, we discussed, it will have some kind of a donut-shaped radiation pattern. So obviously it's definitely better than isotropic radiator. So if logically, if I ask you the gain for a dipole antenna is obviously going to be more when you compare it to an isotropic radiator. Okay, so if I have some antenna radiating its power in a certain beam, if I compare it with an isotropic radiator and then measure its power, then I'll call it EIRP, effective isotropic radiated power. Or I can compare it to the radiated power of a dipole antenna and call it the effective radiated power. PT is fixed for everything. PT is the total transmit power that gets decided by the circuitry in it. So that's the total power you will be feeding it to the antenna. Out of that, what is the power your cell phone is going to receive? That is determined by the gain and the shape and the size of the antenna, which in turn is nothing characterized in the term gain. And the gain, I am saying, can be measured in different ways. Okay, for the same radiating pattern, you can measure the gain with respect to an isotropic antenna, or you can measure the gain with respect to a dipole antenna, a half wave dipole antenna. So in that case, it's called the effective radiated power can be expressed as PT times GTD. Now if you see, if I am computing ERP will be slightly smaller. So you should understand that because now because your dipole antenna is going, it's not an isotropic radiator, it's already directing, it's more like an omnidirectional antenna. It's directing its power only in certain areas, okay, around it, in a certain regions, it's equal power in the azimuthal angle and all that. Okay, so GTD is going to be, when I compare the dipole antenna, it's better than the isotropic antenna, so it will have a gain compared to an isotropic antenna. So now if I want to compare a sectored antenna, some directional antenna with a dipole, that gain GTD will obviously be smaller than GTI. GTI will be larger because your any source, isotropic is the worst form of radiator because it's wasting a lot of power. Okay, when your cell phone is a very small object and it's on one direction, it's wasting a lot of power. So that's why when you compare it to that, you will always be much better. But when you compare it to a dipole antenna, which is not as bad as isotropic radiator, it's going to radiate it. For example, it doesn't have radiation along the axis, so there is so much of power saved. It's only radiating in some directions. So when you compare it to that, your GTD is going to be smaller. It's going to be slightly smaller than the isotropic gain. Okay, so I've written it here. In fact, there is a proper mathematical proof. Your half wave dipole antenna that I told you has a gain compared to isotropic antenna. Isotropic radiates in all directions. So this is actually a sphere. So probably so this is more like a spherical radiation. Okay, so equally in all directions. Okay, and whereas a dipole antenna will radiate mainly like a donut. I said that it's more like a donut, it doesn't radiate like a sphere. So dipole antenna has a gain compared to isotropic antenna. So you can visualize that I've converted all that power, and instead of radiating away in all, wasting it away in all directions, I'm going to give it only in certain directions. So obviously the isotropic antenna has, the dipole antenna has a gain. So you can say that EIRP will always be greater than ERP. So whenever you compare EIRP, so I've already discussed GTI is going to be greater than GTD. So the antenna gain, when you measure it using an isotropic radiator, it's always going to be greater as you compare to what you measure it using a dipole antenna. So if I want to compare, similarly I can take power can be expressed in dBm. Now we know that it can be expressed in dBm. So I'll take dB on both the sides. Okay, I'll normalize, divide this power by 1 milliwatt, this power by 1 milliwatt, and take 10 log on both the sides. So 10 log of this is going to be EIRP in dBm, and 10 log of this term is going to be EIRP by 1 milliwatt is going to be ERP in dBm. Then 10 log of 1.64 is 2.15 dB. So they both are interdependent. So they are not like, when you define EIRP and ERP, they both are related to each other. And EIRP is always more than ERP by 2.5 dB. So it's a decibel. On a linear scale, it will be 1.64 times larger. Now, this is the more important unit. So if you purchase an antenna, you will be seeing these specifications. Let's say you purchase an antenna. What will be more important to you is the radiated power. Yes, that is something you will be feeding to the antenna. Okay. Then antenna properties. Antenna has its own properties. That is mainly characterized by a very important parameter called the gain, and that gain is often expressed in units of dBi. Okay. So that is nothing but your GTI. So that is effective radiated power divided by the, so the EIRP is effective radiated power by directional antenna divided by the radiated power of uh, an isotropic antenna. Okay, so then that gain is what we call the gain of an antenna, and it is expressed, you can compare it with respect to an isotropic radiator and write it as dBi. So if I compare it with an isotropic radiator and then write it, I will call it as dBi. So normally it will be mentioned as 16 dBi or 9 dBi. So these are typical numbers of very highly directive antennas that you will get. Okay, so again, as I said, it can be designed by engineers. It's a parameter that can be designed. So now if you see in the current 5th generation of wireless communications, we are going for what we call as beamforming. So what happens is that, I'll just very briefly introduce to the idea of beamforming. So what happens is that how we do it, we'll talk about it probably later. Okay, as I discussed, when we go to very higher and higher frequencies, when the user is here, as I said that if let's say you're radiating all your power here, he is going to receive a very narrow power. I mean, the area is, aperture area is really, really small. I mean, he's going to receive a very small fraction of the power. But instead, if I can narrowly focus my beam on just one user, I'm going to reduce my beam width to say less than 10 degrees. Okay, so plus minus 5 degrees around the center, or less than 10 degrees, the beam width, let's say, is less than 10 degrees or even lower. Then I can narrowly focus my beam onto just a single user. In that case, I'll have huge gains in terms of the antenna gain. Okay, I'll get a huge gain in the antenna. You'll actually see a huge gain in the antenna gain. Okay, in terms of the antenna gain. So this is how in 5th generation, one of the major claims the engineers were facing with was the path loss, because when you go for higher frequencies, there is a higher path loss. But we said the advantage of going for higher frequencies is that we can generate such very narrow beams of electromagnetic waves. Such narrow beams are not possible, not easily generatable at lower frequencies. At microwave frequencies, it's very easy to generate it. So that's the advantage we claim. Using that, we can actually increase capacity. So that's the whole idea. So when I say increase capacity, you're going to increase the transmit power, which in turn increases the capacity. Okay, I mean, you're going to increase the received power, which in turn will increase the capacity. Okay, so when you purchase an antenna, you should look at the parameter called GTI, the transmit antenna gain, and the units will normally be in dBi. Okay, it's compared to an isotropic radiator. Now, antenna gains are not so often, but sometimes expressed in terms of dBd. So that is, you are going to compare it with a dipole antenna. Okay, now dBd, you can very easily see that dB small d will obviously be less than dBi, because dBi you are comparing it with an isotropic radiator. So obviously you are going to be much better. That's the worst radiator that you can imagine, especially for cellular communications. Okay, so this is obviously going to be the best if you compare yourself to isotropic radiator. But if you compare yourself to dipole radiator, you will not be as high as dBi, but it will be, I mean, if it's a directional antenna, it's going to be more than a dipole antenna as well. Because dipole antenna at the end of the day is a omnidirectional antenna. It radiates equal power around the azimuthal angle. Okay, so again, this is a very standard result. If I give you gain in dBd, you should be able to convert it to dBi and vice versa using the standard result, which is what, I mean, we saw this result earlier itself, because compared to a dipole antenna, I mean, has a gain compared to an isotropic radiator. So when you measure any antenna's gain using comparing it with respect to a dipole antenna, isotropic antenna, you will always have the gain of an isotropic antenna will be more than the dipole antenna gain. By how much? That will be exactly 2.5 dB. So they both have an exact result. So they are interconvertible. If you know one number, you can find the other one as well. Okay. So I've just given a very small problem. I'll upload the slides. You can go through this. I've just taken a problem to find the validity of free space models, the path loss models in the far field region, whether you are in the far field region or not. So you should find what is the far field region. If you know in this problem, the largest dimension is given as 10 centimeter and the carrier frequency is 3 gigahertz. For a 3 gigahertz, the wavelength also turns out to be 10 centimeters. Okay. and so from there you can compute the Fraunhofer distance or the Rayleigh distance to be 20 centimeters. So your far field generally assumes you are greater than 20. Okay, again it should be greater than d, which is 10, and lambda, which is 10 centimeters each. So you are anyways, if you meet this condition, you are automatically meeting these two conditions as well. So d should be greater than d and it should be greater than lambda. So this is a problem I just wanted to discuss for far field region approximations. Now the other more important thing is generally if you see the far field region models, we already discussed that the power goes to 0 as r tends to 0. So we have to actually find this expression is more of, may not be a perfectly valid expression for very low, let's say you are close to the tower, you cannot use that. So in that case, often what they do is, I've already discussed this, we just measure the power at one distance r0 away from the transmitter. So we have, this is the distance to the mobile station. You measure your power at a distance r0. Okay, once you know that power at a distance r0, p of r0, okay, pr of r0 is the received power at a distance r0, then you can predict any power after the distance using this standard result. Okay, so because both of them are in the far field region, so pr of r0 will be equal to pt gt by I'll just write the entire expression. So gt gr by lambda by 4 pi r0 the whole square. This is going to be your received power at a distance r0. Okay, received power at a distance r0. Similarly, you can find the received power at a distance r is going to be, everything is the same except that you have lambda by 4 pi r the whole square. So from this, if I take the ratio of these two, I'll get this result. Okay, so again received power can be expressed in dBm. So here if you see, this expression is important. So all you can see is the received power it will be decreasing at the rate of 20 decibels per decade. As you move away by, if let's say from 1 meter to 10 meters, assuming both of them are in the far field region, then your power levels will reduce by 20 dB. If let's say it was minus 100 dBm at 1 meter, you can quickly say the power level is minus 120 dBm at 10 meters. So for every a decade increase in the distance, your power level will go down by 20 decibels. Okay, so I'll very quickly come to the wave propagation, but before that, yeah. So I think I'll start with the discussion of wave propagation in the next lecture. Okay, I didn't want this lecture to be too lengthy, so I'll just start with the discussion of wave propagation in the next lecture.